Okay. So if you remember, last time we introduced how we can use the inverse of a matrix in several applications. The first application of using the inverse of a matrix was to test the sensitivity of the solution on one of the variable of the vector of results. So if you have vector B, if you just change one value and you want to see its effect on, let's say, x1 or x3, you can do it independently by using the matrix inverse. Because when you write x equals a minus 1 times b, you will obtain a decoupled solution. So you don't need to solve, for example, for x4, then x3, then x2, then x1. You can directly go and solve for the variable you want because you use decoupling through the use of the inverse of the matrix. This is the main first application. The second application that is very important also is to test the L condition of the matrix. So we have seen several techniques to assess nearly if we have a probably ill conditioned matrix or not. We said that we have several techniques. The first one is to find a minus 1. Then we do a times a minus 1. We see if it's close to the identity. Another method is to do a minus 1, then do the reverse another time and see if it's close to a. And another method is to normalize the matrix, then finding a minus 1 and see if the elements of a minus 1 are far from 1 or not. So all of these techniques just can give us, if you want, a slight idea, an idea if the system is highly ill-conditioned or it's well-conditioned. But we said that to be more accurate, we need a number. We need to define it not in a very, if you want, this is the other method is a qualitative analysis, not quantitative analysis. So here we will develop a quantitative analysis to tell me the degree of illness of the matrix in an accurate way. So before seeing how to quantify the condition of a matrix, we will learn how to calculate the norm of a matrix because it will be needed to calculate the condition. So to start with, we have introduced last time the norms. You know that already you are familiar with the magnitude, which is calculated using the Euclidean form, which is radical a squared plus b squared plus c squared. Also, as in numbers, we can define norms also in vectors and in matrix. So if I consider, for example, this vector x, I can find its magnitude by doing radical of the summation of x squared. Another definition of norm will be as follow, is to consider the summation of the different elements of the vector. Now we can define this norm with respect to different subscript p's. Okay, so if p is equal to 1, I just sum the absolute values of x. Okay, if p is 2, I do the absolute value. If it's an even number, no need to put the absolute. And already, if you do it square or to power 4 or to power 6, it's already positive. Okay, but if you have a not number, then you should put the absolute value. And then once you do the addition, at the end you do the whole term times 1 over p. So when p is equal to 2, you get the radicals that you are familiar with, radical a squared plus b squared plus c squared, etc. And you can define norms with different index. Okay, but the most common one is L1, L2, and you are familiar already with L2. And you have L infinity will just be equal to the number itself. Okay, the highest number itself, because if you try to,
Doctor,
yes,
we didn't explain the norm.
we didn't explain the norm last time.
No, we reached إنه ال conditioned إنه
Okay, it's
مثلا.
fine. Yeah, okay. And I thought we covered these two slides. Okay, no problem. I am explaining it now. Okay. Okay. So we have that, as you can see, the norm decreases as p increase. So the highest value of the norm will be for p equal to 1. Higher is p, lower will be the value of your norm. Okay, so for example, if you take p equals to 2, then I will give you an example here. So if you have vector 1, 2, 3. Okay. So the transpose of it is 1, 2, 3 column. If you want to assess the norm based on L1, so just you do absolute value of 1. And I will put here minus, for example. If it's 1 minus 2, 3, then you do 1. L1 will be 1 plus the absolute value of minus 2, which is 2, plus the absolute value of C, which is 3, equals to 6. This is the norm defined based on P equal 1. Okay. Now concerning the norm based on P equals 2, you do radical. So if you apply this formula here, summation of absolute value x to the power p and the whole term to the power 1 over p. So when p is 2, then you have here, so for x2 here, you have sum of xi squared and 1 over 2 here. So you will get, for example, here a radical of 1 square plus 2 square plus 3 square. And you will see that as you increase p, your result will decrease. So the first value was 6, second is radical 14. And if p tends to infinity, what will happen? If p tends to infinity, if you do 1 power infinity plus 2 power infinity plus 3 power infinity, you know that 3 power infinity will be dominant over these two. So these two will be neglected compared to 3 power infinity. And then you do the power 1 over infinity. So you'll get 3. Okay. So this is why as p increases, it will be reduced, and the minimum value will be obtained as the largest between these three, which is p infinity will be equal to 6. Okay. The norm here is it's for a vector. We will define now, George, what is the norm for a matrix. Okay, so in the coming slides, you will see how to define the norm of a matrix. Okay. So now, for matrix norms, we have two possibilities. So first, as we said, we have vector norms, which we defined now, and we have matrix norms. Okay. Now, if you consider for p equal 1, the norm defined with base 1 is the summation of the elements of the vector. So if we take, for example, vector 4, 5, 6, or 4 minus 5, 2, let's say, okay? Then norm 1 will be 4 plus 5 plus 2 equals to 11. And concerning p infinity, we'll take the maximum of absolute value between these elements. So if we have 4 minus 5, 2, then in absolute value, this is the highest one. So p infinity will be equal to 5. Okay. You can deduce again this because the vector is a particular case of the matrix. So now we will see if we have a matrix, how we define the norm. We have two ways of defining the norm for a matrix. So we have several ways, of course, but the main two that we will use in this course are for p equal 1 and for p equal infinity. For p equal 1, this will result into the column sum norm, and it's defined as this notation might be complex for you, but when you do an example, it's very simple. The idea is that for the column sum norm, you will first sum the elements of the column, the absolute value of elements in the column. This is why here, what will very first is you will first fix a row. So for a certain, if you want now the column. Yeah. Let us take an example. 1, 3, 4, minus 2, 0, minus 1. For example, the following matrix. Okay. First, if you want to do the norm based on the column sum, you will now change from column to column. You start with column 1, then go to column 2, then go to column 3. This is why first you fix j. Okay, so you have the outside term is j varying between 1 and n. And for a certain j, now you sum the elements of the column. So now when you take j equal 1, for example, now you will vary I. I is a row number. Okay, so this is I equal 1, this is I equal 2. So now for a certain j, I will sum the elements of the column. So now I will vary I. So I take the I equal 1, then I take I equal 2. And I do the summation from I equal 1 to n of the absolute value of Aij. Okay, so we do now the column sum norm. And if we do it here, we get 3. Sorry, already here we defined 1, 2, 3. So this is I equal 1, this is I equal 2, and this is I equal 3. If we consider 3 by 3, or if we just consider this is the matrix, it's a 2 by 3. So it depends on the example. I think this was 1, 2, 3 columns. يعني نحن الexample أخذناه من الأول this matrix. Okay. So now just you do 1 plus 2, it's 3. Then you go to the second column. 3 plus 0 is 3. And here you take the absolute value of 1. 4 plus 1 is 5. Okay. So now according to this method, the highest element. So after computing summation in each column, you take the maximum over these numbers. This is why they said maximum for j going from 1 to n of the summation from I to n Aij. So to summarize, now here the result will be 5. Okay. So if you want this summation will give you the summation in each column of each column elements. And then we select the highest one, so we take maximum between these elements considered. Okay. Now, if you want to compute the row sum norm, if we take another example, for example, 3, 2, minus 1, 5, minus 6, 8, or minus 8, for example. Now, instead of varying first, now you will fix first the row. Okay, so here you vary I from 1 to n, and then you sum the elements of the row. So here I do 3 plus 2 plus absolute value of minus 1. If I do the row summation, I get here 6. Now I is changed from 1 to 2. And now I do the summation of these elements. 5 plus absolute value of minus 6, which is 6, plus absolute value of minus 8, which is 8. So I have 8 plus 6 is 14, plus 5, it's 19. And I select the largest between the two, which is 19. Okay. In this way, I can define two types of norms, the most frequently used, column sum norm and row sum. Okay. And now we will see how to use these norms into assessing the condition of a matrix. Okay.
Doctor?
Yes.
Doctor, can you please بس repeat the important ideas of slide 23-24 لأنه من 5 دقايق قدرت تفوت كرمال الإنترنت.
Okay. Here in these two slides, we are just defining a way to assess the norm of a matrix. In general, we calculate the magnitude of a vector. You know how to calculate the magnitude of a vector. You do radical a square plus b square plus c square. This is one possibility of norms that we can have. Okay. You have several other possibilities of norm definition. And if you have a vector, okay, if you have a vector, you can define the norm for base 1, 2, 3. What do we mean by this? You just apply this formula that for a vector, the norm of base p is summation from 1 to n of absolute value of x to the power p, the whole term to the power 1 over p. What we will use in this course, the most used one, L2, you know it before, and now we will use L1 with L infinity in this course. Okay. But you should know definition. So I can ask you to find, for example, for a vector, the L3 norm. You just have to apply the formula. It's very simple. Okay, so for example, if I tell you for vector 1, minus 4, 5, calculate the L3 norm, you do just 1 power 3. You always take the absolute value, yani plus 4 power 3, plus 5 power 3. the whole term to the power 1/3. That's it. Okay.
Yes, thank you, doctor.
Okay. So now we define the two types of norms that you will use for matrices. And if we take an application, if we consider the following matrix A, then if I tell you what is the norm of A based on the row summation, you just do take the summation of absolute values of these elements. So it's 1 plus 2 plus 5 for the first row. You get 8. For the second row, 7 plus 0, 3 plus 6 is 13.3. And for the third row, 12 plus 1 plus 0 is 13. Then once you are done with this, you take the highest element between them. And then you say, this symbol, A infinity, is for row summation. Okay. And symbol A1 is for column summation. So now if we compute the norm of A based on column summation, we sum first elements for each column. And then we select the maximum between them. So here, if I do 1 plus 7 plus 12, it's 20. 2, and always just remember, never take the negative sign. So you take the absolute value, and minus 2, you take it as 2. 2 plus 3 plus 1, 3.3. And 5 plus 6 plus 0, 11. The highest between them is 20. So we can say that based on column sum, we have that the norm is 20. Okay. Now, how to use these norms? We will now introduce how to calculate the condition of a matrix, and you will see how the condition of a matrix will be an index of the degree of illness of the matrix. So if it's well conditioned, if it's ill conditioned, etc. So how to quantify the condition? Previously, we developed techniques, but these techniques were not able, if you want to just give us an answer, a strict answer, and this is the condition of a matrix. These techniques just help us to say if it's probably ill-conditioned or very ill-conditioned or well-conditioned, okay? So now we can say in numbers what is the condition of the matrix. The condition of a matrix can be calculated as follows. It is the norm of matrix A times the norm of matrix A minus 1. Okay, and it can be based on column summation or row summation. In general, we tell you what to use. If not, to be on the safe side, you consider the if you want the highest one. Okay, because we will see that once we determine condition, we will be sure that the measure of solution error will be smaller or equal to the condition of A times delta A over A in norm. I will explain in detail what this means. So first, to calculate condition of A, I should find A minus 1. So as we said, the inverse of a matrix is very important in calculating the condition number. Because before being able to calculate the condition number, I should find the inverse of matrix A. And then I say that the condition of A is the norm of A times the norm of A minus 1. And it will be minimum, it will be equal to 1. If it's equal to 1, this means that it's a very extremely well-conditioned matrix. Okay, and this is the ideal possible scenario. In general, it will be higher than 1, and higher is the condition number, higher is the illness of the matrix. Okay, so in this way, you can compare illness of the condition of different matrices by calculating their condition number. And higher the matrix having the highest condition number will be the highly ill-conditioned one. Okay. So why this will be an index? Because we can demonstrate, and you are not responsible of the demonstration. You should just know this. Okay, because this is a mathematical procedure that is learned to demonstrate. You should know that the measure, if you do a certain, if you have a certain system A times X equals to B. Any variation in B, okay, will affect your result for X. Okay. Now, you expect in general, if your matrix is well conditioned or very well conditioned, that if you vary B but by a certain percentage, you will get the same variation nearly in X. This is what you expect. But if your matrix is highly ill-conditioned, you might have very bad results. Okay, and to be able to know if this will happen or not, we will develop the technique of calculation of the condition number. And when we calculate the condition number of the matrix, we will have an idea about the amount of errors that can be induced. How? We can demonstrate mathematically that the measure of solution relative error. So when you do solution for X, okay, this solution error will be smaller or equal. So the maximum error induced is equal to condition of A times, if you want, the delta that can be done to A or to B. Yani, if you change A by a certain percentage or you change B by a certain percentage, okay, you can say that the measure of errors that will be induced in X will be smaller or equal to the condition number of matrix A times the variation that A will undergo or B, okay, over the norm of the variation over the norm of the matrix. Okay, what do we mean by this? To be more clear, if you vary B 1%, okay, if you vary B vector by 1%, if your condition number is 1, then also you will have same percentage of variation in X. But if your condition number, for example, is 10, then if you vary B or A coefficients by 1%, then expect to have 10% of variation in X. And higher is the condition number, higher is the variation between these two, okay? So in this error, you can have, in case the condition is very high, for very small percentage change in B, you will have a very high percentage change in X. And already, if you remember, when we introduced the concept of systems, we had 4 possibilities: no solution, zero solution, infinity of solution, and ill-conditioned system. For ill-conditioned system, we have seen together an example where if we changed by 1% the value of one of elements of B, the solution changed by for 1x by 400% and 100%. How we can explain this? We could expect this by calculating the condition of matrix A in the system AX equals B. And this will be a warning for us. So if we calculate the matrix, the condition number of A, and we obtain a very large number, we say, be careful. We will have a high error if we don't take enough digits in our numbers. We will see this in an example, okay? And after doing the example, I will go back to the slide to read this so that you can understand it in a better way. For example, if you consider the following case, okay? In the following case, we have A times X equals to B. Vector B is defined, and we have 4 digits for elements of B. So here we say that we know our elements up to 4 digits. So T is equal to 4. Now, if I solve, okay, if I solve this system, I have, using the techniques we developed together, we can use Gauss elimination, we can use LU factorization, you can use what you want. If you solve for it, you will get the system 1, 1, 1, 1. Now, let us say I want to change just the last digit of elements of B. Yani I'm doing a change of less than 1/1000. Okay? So for example, instead of 32, I will put 31.99. Instead of 23, I will put 23.01. Instead of 33, I have 32.99. And instead of 31, and also you don't have to vary all, maybe you vary one, just one. If you just vary one, all solution will be affected. So, and if you solve, you will see a very large difference between the results. This means that if I just do not trust the 4th digit, so here I don't trust only the 4th digit of my of B. If I just don't trust the last digit of B, then I will have a completely different solution for X. And I cannot trust any digit because here this is closest 0.18, it's closest to 0 than 1. And 1 is different than 0. And even I cannot trust this, the first digit, I cannot trust it. So I can say that my solution is uncertain. And the degree of uncertainty is very high. Okay, so that I cannot trust any of the digits. And I cannot rely on such system to get X. Then what I can say if I have to deal with this matrix, so if I cannot play with it, then my only solution will be to increase the number of digits to take. So instead of taking 4 digits for B, I will take 6, 7, 8, etc. Now, to know exactly how much I should take, I should know what is the error involved. I can expect how many digits I can trust using the following method. Okay? The method is to calculate the condition of A. So let us together first find the condition of A. And then once we have the condition of A, we can say that the number of untrusted digits will be equal to log base 10. So on your calculator, you do log base 10 of condition of A. The number you get, which is here between 3 and 4, up to 4 digits, will be the number of digits that you cannot trust. And here, you got that for this condition number, the worst case scenario will be to not trust 4 digits, which is really bad. And this is what you obtained here, because in this example we have taken together, I could not trust any of the digits of the solution. This is 1, 2, 3, 4. So I can say then that in the worst case scenario, the number of digits I can trust will be the number of digits I can read, T, minus C. Now, since T was equal only to 4, this is very bad. I cannot trust any digit. And this is the result I obtained. 4 minus 4 is 0. So I can say here, I cannot trust my solution. Okay? So, but keep in mind that this will not be always the case. This is the worst case scenario. So if I give you another example, if I change B and I change it by 1%, مش ضروري كمان على طول إنه I cannot trust 4 digits. This is the worst case. But because I have this possibility, I should be aware of it. And this will give me the worst scenario. And in the worst scenario, I need to eliminate 4 digits. I cannot trust them, and I can read the remaining one. So this is why here I will say I cannot work only with 4 digits in B. I should work with minimum 5, and higher is the number of digits I work with, I can be more comfortable. So if I work with 6, 7, 8, so let's say I work with 7 digits, T equals 7, I say I can at least trust the first 3 digits. So then I can trust 7 minus 4 equals to 3. Okay? Then it might be acceptable in this case. Okay, so it depends on my application, on the degree of accuracy that I desire. Then I will decide if it's fine for me to continue with this or not. If not, I should increase the number of digits. Okay, sometimes it depends on the application. If it's an experimental application, I have a limit maybe, so it will be then more challenging. But at least this method will give me an idea about the error I might have.
Here.
Yes.
لما نعمل احنا T minus C we are taking T يعني number of digits اللي عنا اياهم عم ناخدهم.
Yes.
والC
يعني
هي شو يعني؟ Yes.
السي هي اللي بتجيبها من الكونديشن نمبر. هون مثلا رح ارجع اعطي اكزامبل. If you now decide to work with 6 digits, T هو number of digits here. So here you are knowing your numbers up to 6 digits. So here T equals to 6. Okay? السي بتجيبها من الكونديشن of A. يعني انت هلا حنعمل calculation للcondition of A سوا. You get the number.
Yes.
Once you get it, okay, you say that condition of A is equal to 10 to the power C. So how you get C? C is simply log 10, log base 10 of condition of A. Okay.
Yes, clear. Thank you, doctor.
Okay. So now C didn't change here because A is fixed. بعدها بنفس الماترix. What we changed is the number of digits in B. So now T is equal to 6. Okay. And then I can expect that in the worst case, I can trust 6 minus 4, which is 2 digits. But as I told you, I can have a better case, and depending on B. Let us check this for the same example. إذا بناخد here and we just vary the last digit. What you will get here is that as expected, you can trust, okay, you can trust at least 2 digits, because look, you have here 0.9. If you round it, it's 1. You have here 1.0. You have here 0.9. It's nearly, if you round it, it's 1. And here you have 1.0. So it's true. I can trust in this case 2 digits. Okay. Keep in mind, I can trust more, but in the worst case, I can trust just 2. Okay. So if I give you another example, here, for example, I changed B, but I'm still working with same A. I have same value of C. But as we said, C, the maximum number that I should not look at is 4 digits. Okay. But I might have a case for certain B's, I can trust more. I can trust more than T minus C. But T minus C in some worst case, in a certain worst case, I can trust just T minus C. Here, for example, I gave you another value for B, and also I just changed the last digit. I played with the last digit. So if I just take here, I'm taking T equal to just 3. And if I have a bad scenario, if I choose B in a bad, إذا كانت B set up in a bad way, that the worst case scenario will be that I cannot trust anything. بس إذا بنجربها هون, the solution was not very bad. minus 1200 صارت minus 1282, but at least you can trust 2 digits here. 2000 home 2136, you can trust at least this one. For 500, you can trust at least this one. So what you can say here is that I might have cases where I can trust digits, okay? But since I have the possibility of a worst case, another example, the case was even worse. So I cannot trust 4 digits in the case that I gave you before. So what I want to tell you is that this is the maximum error that I can have. This will give you the maximum possible error. This is why it is a good index. And if in case the maximum possible error is relatively small, you are on the safe side. Okay? Because keep in mind, it's not equal, it's smaller or equal. If you go back to this slide, they said the measure of solution relative error can be smaller or equal. Equal is the worst scenario. Okay, so I have cases where it's smaller, but I can have also a worst case scenario where it's equal. So to be on the safe side, we try to reduce as much as possible, if possible. Sometimes we have this matrix and we want to work with it. We calculate its condition. So we fix the condition number. Now we will play with number of digits. Let's say I know the accuracy desired, then I say I need to take more digits in B to be on the safe side. Okay, so the general rule, if coefficients of A, okay, or B, A and B, are known to T digit precision, so the round of error is of the order of 10 minus T, and condition A is calculated and can be written as 10 to the power C, then the solution X may be valid to only T minus C digits, which is equivalent to saying that the round of error is of the order of 10 minus T plus. Okay? Now, في شيء مش واضح about this? Any question on this? Yes?
دكتور
No.
يعني احنا هيدي ال T minus C
No.
هي digits of X يعني that we can trust.
Exactly. Yeah. هي number of digits in the solution that we can trust.
يعني compared to the actual solution.
Yes, of course. يعني انت
Okay.
كل الباقي يعني انت اصلا اكيد compared to the actual one يعني كل الباقي بعد ال 4 digits you might have very different results. اوكي من بعد t minus t معقول يفرقوا كثير ال results. اوكي
دكتور بالاكزامبل that you gave at the end
yeah
بس وقت كان هن 3 digits we couldn't trust وهن السي
هيدا اللي بدي اقول لك اياه حسن. انا اعطيت هيدا الاكزامبل تقلكم انه تي ماينس سي بتعطيكم الورست كيس سيناريو بس مش ضروري على طول انه I cannot trust 4 digits. اوكي يعني نحن هون ثاقبت انه اللي اعطيتكم اول شيء worst case scenario طلعت انه I can't trust any of the digits. مزبوط. هلا هون
مزبوط.
هيدا الاكزامبل if you calculate t تنقول t هون is 3 وc بعدها 4 يعني انت اذا ثاقب حظك انه هيدا الورست كيس سيناريو you cannot trust any of the digits. اوكي بس برجع بعيد انه الايرور smaller or equal مش على طول equal. يعني هون اعطيت اكزامبل ثاني مزبوط انه سي اكبر من تي يعني مبدئيا انت اوريدي بتكون aware of this انه I might have large error بس بهيدا الاكزامبل for this particular case of B ما كانت الايرور يعني when you did calculation and you compared انه you can't trust 1-2 digits بسهوله. يعني if you say one digit اكيد you can trust it. يعني هون الاول digit هو ذاته للكل 1 1 2 2 يعني هيدا example انه انت لقيت الورست كيس سيناريو بس مش يعني انه على طول حيكون عندك الورست كيس سيناريو. just to tell you this. بس بالنهايه بمجرد ما يكون في عندك هالprobability انه